Okay, so let us start this last section of field extensions. Galois groups over the rationals. You may remember that when we started studying field extensions, when we started looking at roots of polynomials, we came across this result that if f is suppose some field and fx is a polynomial over f that has positive degree n, say, then there exists an extension of f, say E, which contains all the roots of this polynomial and such that it's a finite extension of f, and the degree of E over f is at most n factorial. And at that time we mentioned that this bound of n factorial is actually attained. And in the previous section we saw that, okay, that the bound of n factorial is actually attained, that there is a polynomial over field of rational functions actually, for which the splitting field is in fact of degree n factorial, where n is the degree of the polynomial. Now the thing is that we want something similar to happen not over the field of rational functions, which is somewhat not so familiar to us. It's not as familiar to us as the other fields with which we always work. For example, the field of rational numbers, real numbers, complex numbers. So we want the similar thing to happen over this familiar field, the field of rational numbers. Okay, and that's why we now have this theorem. So let's see what it says. It is going to say something similar. Similar means we are now going to have a polynomial over the rationals such that the splitting field of that polynomial over the rationals is going to have degree exactly equal to the factorial of the degree of the polynomial. This, however, we won't get for a general n, but for a prime number. So this is how the statement goes. Let P be a prime number and let Qx be a polynomial with rational coefficients. In other words, Qx is an element of this ring. Also, Qx is an irreducible polynomial and its degree is that prime P. And there is one more condition imposed on Qx, that Qx has exactly two non-real complex roots. In stating these conditions, we are assuming the fundamental theorem of algebra, which says that any polynomial whose coefficients are complex numbers has only complex roots. Okay, so that's why here also the coefficients of Qx are complex numbers. Rational numbers means after all complex numbers. So all the roots are going to be complex numbers. But the condition now is that exactly two non-real complex roots of Qx are there. The other roots are all real numbers. Then the Galois group of Qx over Q is going to be the symmetric group of degree P, Sp. And as a result, the splitting field for Qx over Q will have degree exactly P factorial. Let us now see how we can prove this. So the proof starts by considering the splitting field of Qx over the field of rational numbers, and let us call that splitting field K. Let K be the splitting field of Qx over Q. Okay. And now let us consider a root of Qx. So if we consider a root alpha of Qx, any root of Qx, then what shall we get? That root, first of all, will belong to K, because K, being the splitting field of Qx, contains all the roots. Let alpha in K be a root of Qx. Then the text says that by a previous result, and that previous result is Theorem 513. The degree of the extension of Q obtained by adjoining alpha to Q over Q is equal to P. But exactly how are we getting this? I mean, at once it doesn't really become clear. So let's see what went on here behind all these things. What is exactly going on? See, alpha being a root of Qx means what? It means, let me show it on the other side. It means that if we substitute x equal to alpha in the polynomial, we are going to get 0. That's what it just means. So now we have this. So alpha satisfies the polynomial Qx. Now Qx, being an irreducible polynomial, cannot be 0. That means Qx is a non-trivial means non-zero polynomial that alpha satisfies. So that tells us what about alpha? So alpha is algebraic over Q, because that's what being algebraic means, satisfying a non-trivial polynomial. On top of that, Qx is also irreducible, since, not this Q, since Qx is irreducible as well. So by this theorem, first of all, the extension Q alpha is going to be a finite extension of Q, because alpha is algebraic. And the degree of this extension will be the degree of an irreducible polynomial over Q that alpha satisfies. And this Qx is such a polynomial. And that is why this degree is equal to the degree of that polynomial, that is degree of Qx, which is P. So that's how we are getting this. Fine. Now we have next this thing, since K is having the extension Q alpha as a subfield, and this of course contains Q, it follows from the very first theorem of field extensions that the degrees of these things are related by an equation. And that is, I think, 511. It should be 511. Yes. Since this, it follows from Theorem 511 that what do we know from that theorem? The degree of k over q is equal to the degree of k over the intermediate field, that is q alpha, times the degree of q alpha over q, right? And this is p, times p. So because of this, p divides this degree of k over q. All right. Now we next consider the Galois group of the polynomial qx over q. Since k is the splitting field, okay, again we are going to need one more theorem. Now if G is the Galois group of qx over q, then there is a relation between the order of G and the degree of k over q. They are same actually. And that comes from this theorem 564. Then the order of G is equal to the degree of k over q by theorem 564. So that means what? That p divides the order of G. Now G is a finite group whose order is divisible by a prime number p. So Cauchy's theorem can be applied here. Cauchy's theorem from group theory. Thus, by Cauchy's theorem, what does that theorem say? It says that then G has an element of order p. G has an element, say sigma of order p. Do not forget what sigma is. Sigma is going to be an automorphism of k. Alright, so we get this much just from these fields and all these things, but so far we have not used that other hypothesis that our polynomial qx has exactly two non-real complex roots. So we are next going to consider that. Let alpha 1 and alpha 2 be the two non-real complex roots of qx. That means the other roots are going to be all real numbers. And how many others will be there? P minus 2. That's because our polynomial qx has degree p, so it will have exactly p roots. Counting multiplicities, that thing is there. So besides these two, there will be p minus 2 more roots. So the other roots, let us call them alpha 3, alpha 4 and so on up to alpha p, are all real. All right. Okay. Now we are going to recall the result of a previous exercise, and that is this exercise. If you go back to that exercise, you will see why we are getting what I am going to write now. By exercise 13 of the third section, that is section 5.3, we have alpha 1 equal to the complex conjugate of alpha 2 and alpha 2 equal to the complex conjugate of alpha. Actually, it's enough to write only one of this because the other one automatically follows from that. But anyway, the author has written both just to show how the roots are related to each other. And of course, because the other roots are real, so their complex conjugates are themselves. Also, alpha I, bar obviously denotes complex conjugation, is alpha I itself for all I greater than or equal to 3. So now what does it mean? What do all these things give us? So you can now think of the conjugation map itself. That's what the author did. That map interchanges alpha 1 and alpha 2. That means it maps alpha 1 to alpha 2 and alpha 2 to alpha 1 and fixes every other root of qx. And we are going to give it a name also, say tau. Thus, if tau denotes the complex conjugation, then tau maps alpha 1 to alpha 2, alpha 2 to alpha 1 and fixes all the other roots of qx. Now the thing is that this tau actually corresponds to a permutation of roots, and that permutation is the transposition 1, 2. That's because if you think of these maps as maps among the roots, then they themselves also become permutation when we restrict your attention to only the roots. But it's better to say that they induce permutations of the roots. And the permutation that this tau induces is the transposition, which interchanges the symbols alpha 1 and alpha 2. When we are thinking of permutation, then we treat these alphas as just some symbols, like what we do in permutation group. But what about that sigma? That sigma is also sitting there. No? In the previous paragraph, we saw that because of Cauchy's theorem, G has an element sigma of order P. That sigma also induces a permutation of the roots. And the author has written another paragraph on this. In general, this is what he wrote. The elements of G induce permutations of the roots of QX. The element tau induces the transposition. One comma two, the 2 cycle. Transposition means 2 cycle. And the element sigma, because it originally has order P in G, induces accordingly a permutation of order P again in the symmetric group of degree P. SP, because there are P roots, so if we are talking about their permutation, then essentially we are talking about SP. But the only elements of order P in SP are the P cycles. Keep in mind P is a prime, okay? Since the only elements of order P in SP are the P cycles. So the permutation that sigma induces in SP is also going to be a P cycle. The permutation sigma induces in SP is also a P cycle. Which P cycle we don't know, but some P cycle. Since the transposition 1, 2 and a P cycle in SP generate the entire SP. Now this is a fact which is we haven't really exactly proved this yet. We have seen something similar in the section on permutation groups. But let me first write what the author has written and then we will discuss about it. So because of this, what will happen that G will be equal to SP. Actually, there are some other steps also in between, but I am leaving those things out. It's there in the text and I want you to figure out this portion. What exactly is the author saying? You may have noticed that I have not really given any elaboration on this other than what is there in the text. I haven't really done anything extra here, and this has its purpose. I want you to figure out. It is a little vague, no? I mean, we are suddenly saying that the complex conjugation, yes, of course, we know what complex conjugation is, but the complex conjugation induces a permutation in SP. These things are also clear, but it's not exactly rigorous. So I want you to make these things rigorous, and I also want you to figure out what it is that the author has written here. How exactly are we getting G equal to SP? And one more thing is that this fact is not proved for us. Okay, it has been taken for granted, but it is true, and something similar has been proved elsewhere. In the section on permutation groups, if you recall group theory, there we came across one exercise which asks us to prove, and we did prove actually, we solved that exercise. It says this: consider the symmetric group of degree n Sn. In this, you consider this transposition that we have considered here, and this specific n cycle in that exercise we are asked to prove that these two elements generate Sn itself. In other words, the smallest subgroup of Sn that contains both these elements is Sn itself. That's what generate means. And that similar thing is being said here. Here, however, we do not exactly have this, where in place of n you have p, but some p cycle. There are exercises, however, at the end of this section that will take care of this thing. But the fact now is that we have got G equal to SP. And again, is this equality literal equality, or is this only an isomorphism? That also you try to figure out. Now, the moment we get this, that means the Galois group is nothing but SP, and that is why the degree of the splitting field of our Qx over the field of rational numbers, because of this fact, is going to be exactly equal to p factorial. So, the proof of the theorem is over. Now, let us see one application. Now, say we want such polynomials so that we can apply this theorem. We want to have an irreducible polynomial whose degree is going to be a prime number. Additionally, we also want the polynomial to have exactly two non-real complex roots. The other roots should be real. Then the splitting field, or then the Galois group of the polynomial over the field of rational numbers will be equal to this, where p is the degree of the polynomial. And we are now going to see an example where p is 5. Say, let p be 5 and consider the following polynomial. and this polynomial is of course going to have degree 5, and it is 2x to the power 5 minus 10x plus 5. We need to also maintain the fact that it has to be irreducible besides having that prime degree over the field of rational numbers Q. Now it has prime degree, fine, so the degree is 5. Is it irreducible? Let us apply Eisenstein's criterion. You see that we have the prime 5 which divides all the coefficients of this polynomial except the leading coefficient. That's not divisible by 5. The other coefficients are divisible by 5, and additionally the constant term is not divisible by 5 square. That means this polynomial satisfies the hypothesis of Eisenstein criterion with the prime 5. So we can simply write by Eisenstein criterion Qx is irreducible over Q. Okay. But we need to also see that this Qx has exactly two non-real complex roots, and for that we need to use calculus. So what we do, we first differentiate this with respect to x, because after all this is a function, right? This is a polynomial function which is a real valued function of a real variable. So if you differentiate this with respect to x, here you consider the first derivative. It will be 10x to the power 4 minus 10. Now if you set this first derivative equal to 0, then you get x to the power 4 equal to 1. So x is plus 1 or minus 1. These two are critical points of this function. Excuse me. And now we calculate the second derivative. So we are using the second derivative test for finding maximum and minimum values, local maxima, local minima, those things. Now if one calculates the second derivative, one gets what? 40 x cube. So evaluating the second derivative at say minus 1 first, we will get, because cube is there, it will be minus 40. This is less than 0. So Qx has a local maximum at x equal to minus 1. Next, let's calculate the second derivative at 1. So that becomes 40, which is greater than 0. So Qx has a local minimum at x equal to 1, and that's it. So in order to achieve this local maximum and local minimum, the graph of Qx turns out to be somewhat like this. I haven't drawn the exact figure, but it roughly is going to look like this. So something like this, okay. And when it's going down on this side, it doesn't come up, and on this side it doesn't come down. Okay, in this wavy nature is seen only here in this region. So from this is your 1. So where you have a local minimum, and at -1 you have some local maximum. From this, one can see that there are exactly 3 real roots. However, the polynomial has degree what? 5. That means 2 more roots should be there. These 2 roots, however, are not real. Thus, Qx has exactly 3 real roots, i.e., it has exactly 2 non-real complex roots. And that's why now we can use the conclusion of our theorem and say that the Galois group of this polynomial over the field of rational numbers is the group S5. Okay. And because S5 is not solvable by results of the previous section, the roots of this polynomial cannot be expressed as combinations of radicals of rational numbers. We know that these roots are real and there are non-real complex roots also. However, you cannot express those in terms of plus, minus, product, division, square root, cube root of rational numbers. You cannot express them in terms of those in some manner. No, that is not possible. That's what the results of the previous section say. So these values are available, but they won't be expressible in that way. Okay, so this is one application of the theorem that we saw today. And this is where actually everything kind of ends here that we have in this book on field extensions. The exercise problems are still there, which we will solve, but the theory part is over. And I would have to stop here itself. And what do we have tomorrow? Oh, tomorrow again we have trigonometry of class 11. So that's just it. See you tomorrow with trigonometry. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.